Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering the Advanced Mechanics Module 5 of HSC Physics, Inquiry Question 2, Circular Motion, and we're going to be going through this particular syllabus outcome, analyze the forces acting on an object executing uniform circular motion in a variety of situations. We're going to be focusing on a mass on a string. Okay, so our lesson intention today is to investigate the forces acting on a mass attached to a string undergoing uniform circular motion. Your success criteria of this lesson is to analyze qualitatively, so with numerical data, the relationships with our mass on a string. Okay, so let's get into it. Okay, so let's begin our analysis. A ball on a string. You can sort of already see the different types of vector forces or the different vectors that are involved when you spin a mass object on string and you perform circular motion onto it like so. We did a force vector diagram in our previous lesson in analyzing it. So you can see that we have the tension force pulling up to the center point here. We have the gravitational weight force pulling down. And the reason why it's in circular motion is because it has centrifugal acceleration. We said from our previous lesson, the centrifugal acceleration is contributed by the horizontal component of our tension force. Now, there's actually a couple of scenarios that you can look at with a ball on a string. Okay, so if we actually look at some of these scenarios, we have two types. We have uniform circular motion when the object is being spun directly horizontally, meaning by we have a constant vertical height. And then we have another scenario which is about you rotating vertically like so. Let's try and firstly compare the difference. So this will do as a nice recap from our previous lesson. Firstly, we said that if an object is undergoing circular motion on a string, there is a gravitational weight force, and that's represented as m mass times acceleration, in this case from gravity, so we write little g here. It's being pulled towards the center, that's our tension force, okay? We also said that the tension force can be split up into two components, a vertical component, like so, and a horizontal component going in this direction here. Now, if we look at the triangle that we've drawn, so this is the angle we've established. That's sort of like our right angle triangle, if you can sort of picture. This component is cos, or is it cos theta? Okay, so the force on the vertical component that we have here, or what we call Fty, as you can actually see, we have the force component. The angle is drawn like so, so let me just show you the angle again to make it nice and big. This is our tension force. This is the tension force that's going to counteract our weight force. If you actually look at this here, it's tension force times sine or cos theta. Not the one we see here, that's incorrect. Okay, so you have the hypotenuse, you have the adjacent side, so we have this as sine theta. This is the component that cancels out this gravitational weight force component. So the point here, okay, is the horizontal component. And the formula for that is Ft sine theta, as this is the opposite side of the angle. Okay, this just so happens to be our net force and our centrifugal force of our motion. So in this case, mv squared over r. So that's what we're dealing with if it's a horizontal spinning pattern for our mass on a string. Things get a little bit different when we are considering it in a vertical component. So there's actually two things that are occurring for the vertical component. There is the top part here, and there is the bottom part here, okay? So let's think about what's happening at the top. At the top of the spin, the tension force is pulling our plane down, okay? And also there is a gravitational force pulling this plane down. When we come down here though, the tension force is pulling, I'll do it in a different color. Okay, so for our bottom scenario, we are exerting a tension force to pull our plane up, and we have a gravitational weight force pulling the object down. Why do I say it for this one? Because gravity is pulling it down here, but the force of the string is pulling it back up, whereas this one, it's pulling it down. So what that actually means is there is some form of change in speed. There are some considerations in the change in velocity, because the velocity down here is definitely not the same velocity up here. There is going to be some fluctuations as you go through parts of that spin. So a lot of the scenarios we'll look into, we don't really look into this type of scenarios. We tend to look at the horizontal component only. Okay, so when we're looking at mass on the string, we're looking at a conjugate pendulum. So tension from the string will counter the weight force. As we said, it is the component of the tension force that will counter it. Okay, so there's a couple of things you can use. You can use the following equations. So you have tension force equals to our net force sine theta of sine theta. So that's a way we can work out tension force with the net force. So a relationship between here and here. Or you can use cos theta. So this bit here, I'll use a different color again. We can use cos theta, this bit here and this bit here, to find a relationship between the weight force and the tension force. Okay, if we want to find the net force with information of the gravitational force only, we can use the following formula or the following ratios. Okay, so those are all the different combinations you can use. So Ft stands for friction force, or not friction force, tension force. F net is the force acting towards the center. That is also our centripetal force. So you can also represent the net force using this formula here, mv squared over r, formula for centripetal force. And then we have the force due to gravity. Now, same as the previous lessons, we're going to go through the calculation questions as a separate video. There's going to be another question on bank curves as well, as a special little practice, so keep on track with that. Okay, so we've gone through quite a lot of different scenarios. We've gone through how cars move around a horizontal circular bend or circular spin. So that's the formula we can look at. The centripetal force is due to the static friction. Remember, this was the static friction of the road. Okay, so that's our contributing centripetal force factor. If it's on a banked track, we don't actually need to use friction, or is not required, so to speak. And for most of these questions, we tend to ignore friction, but you can have questions where it might ask you to find parts of friction involved. unlikely, but that's the case. So the contributing factor, if we're on a bank curve, so on a inclined plane and a car going circular motion around, that's contributed by the horizontal component of the normal force. We also said for a mass on a string, if it's being rotated horizontally along like so, okay, it's the horizontal component that we can use to find the motion of the object. Now, obviously this angle and this formula here is really dictated by where you get that angle. So if this is theta here, and we move along here, then the actual formula is ft sine theta. But if the angle we find is more like here, okay, then you can use ft cos theta. So I'm just going to scribble this one out, because this really depends on where the theta sign is, okay? And then lastly, we have mass on a string for the vertical direction at peak height, okay? And that is contributed, so if we are spinning an object around like so around this way, at this very point, at the very peak, it's the tension force plus the gravitational force that gives us our centripetal force, like so. So that gives you a nice scenario of all the different conditions or scenarios that we see using what we talked about from the syllabus outcomes. All right, so we have one additional scenario that we can talk about. We also discussed this in one of the previous lessons, and that's centripetal force, centripetal force, sorry, acting on a gravitron, okay? So we talked about, for this scenario, that we have gravitational force pulling you down. The reason why you're not falling down is because when you're attached onto the surface, the friction force is opposing the motion going down. Now, a lot of people might confuse this as the normal force. No, because the normal force is always acting perpendicular to the contact spot. So if we have this person here touching the wall of the gravitron, you can sort of think their normal force is being projected perpendicularly out of that surface to this machine here. The reason why they are not falling down because of the weight force is because there is sufficient friction on this gravitron that's opposing that motion. Static friction in this case. All right, so there is that. You can actually do a little challenge for yourself. All you need is a little marble and a cup. All you have to do is start spinning the marble around the cup, and you should find yourself to demonstrate the exact same phenomena of the gravitron. Okay, so give it a go, see if you can do it. And that takes us to the end of this lesson here. Like I said, the following video is going to go through the calculation questions from this lesson. There aren't a massive amount to go through, but there are also some nice past paper questions that you can try, with the following links also listed as well. Anyhow, thank you for joining me for this lesson. If you found it useful, give it a like and subscribe if you haven't done so already, and I'll see you next time.